Is it audible? Okay, good evening. So let us start. Okay. So that is vibrating string. So here actually the general solution of a vibrating string, right, which is most apt for the solution, we proved that is, so y of x comma t is equal to c1 sin px plus c2 cos px getting multiplied by c3 sin cpt plus c4 cos cpt. So this is the general solution, right? And the string is, so initially it was tied like this, and at this point there is no displacement, whatever may be the time it is, that is y of 0 comma t is always comes out to be 0, and y of L comma t is also comes out to be 0, because this won't move under any circumstances, because these two are tied up. Got it? And then initial displacement is given in a certain equation format. That equation, what he mentioned was, so mu x into L minus x. So this function is mu x into L minus x. Yeah. And initial velocity, obviously it is going to be 0, dy by dt at t equal to 0. So this is also always 0. So these are the four different conditions, whatever he has given, right? Now let me write down the problem statement for the completeness. So that is, the problem statement is, a tightly stretched flexible string has its ends fixed. A tightly stretched string, has its ends fixed at x is equal to 0 and x is equal to L. Has its ends fixed at x is equal to 0 and x is equal to L. 0 and L. At time t equal to 0, the string is given a shape defined by, at time t equal to 0, the string is given a shape given by the equation f of x is equal to mu x into L minus x. Where mu is a constant and then it released, where mu is a constant. And then it is released. It is released. Find the displacement at any point of x. Find the displacement at any point and at any instant. So what he asked was, he asked us to find out y of x comma t. So this is the displacement at any location x and at any time t. For this particular string, initially it was stretched like this and is having a displacement of mu x into L minus x. This is the equation of this particular curve. Now if this is the displacement what it was given, and the initial conditions are y of 0 comma t, so that is at location 0 at any time t is always comes out to be 0, and at location L at any time t this is also again equal to 0, because these two are tied to the point or nail there, right? And then the initial velocity for the string will always be 0, because there is no movement, hence there is no velocity. You are holding like this, that means at any point on this particular line the velocity is coming out to be 0 at time t equal to 0. And one more condition is, that is initial equation, that is so this is y of x comma 0 is mu x into L minus x. Y of x comma 0 we mean at any time t, at time t equal to 0, at any location of x distance, the curve is given by mu x into L minus x. So these are the 4 different boundary conditions it was given in this particular problem statement. Now he asked us to find out y. So this entire problem statement is described in this small diagram. Got it? Okay. Any questions on this understanding the problem statement? Any questions? Okay. Now actually, based on this understanding, so we know that any general solution of the vibrating string is always given by this equation, that is y of x comma t is equal to, boundary. What is the doubt you have, Avinash? Any doubt, Avinash? Okay. So boundary equations. See this. There are 4 different boundary conditions we need. Why we need 4 different boundary conditions is we have C1, C2, C3, C4. 4 different arbitrary constants are there. So you have to have at least 4 different boundary conditions. So in that, by looking at the problem statement itself, you can make out 2 different boundary conditions straight away. That is, so the string is tied like this. So if it is tied like this, so even if you drag whatever may be the displacement, so this will always tied at 0. That means there won't be any vertical displacement either in the top or in the bottom, right? There won't be any vertical displacement at this particular point. Exactly in the similar manner, there is no vertical displacement at this point. Now, at any instant, this is y actually. So this is y. So y actually is 0 at this point and y is 0 at this point as well. So y of L comma t is equal to 0. Y of 0 comma t is equal to 0. Now this t is a variable and first value is always 0 because x location is 0 and here x location is L. And t, that means at any time, whether it is equal to 0 or non-zero, it doesn't matter. Always it is tied to 0. So this is also tied to 0. Hence, these 2 boundary conditions, y of 0 comma t equal to 0 and y of L comma t equal to 0. These are understood. And then, because you are holding initially, the initial velocity is also equal to 0. That is dy by dt is again 0. Derivative with respect to time will give the velocity. So displacement with respect to time rate of change of displacement is called the velocity. That means at t equal to 0, the velocity is again 0 because you are holding like this. It's not moving yet at t equal to 0. Hence, the velocity is again 0 because the position is static now. And then one more equation is initially, so you wanted to have a displacement. Why? Because see this is a string. Now if you want to have the wave equation, you have to give a certain kind of displacement to it. Like you drag like this and leave it. Then only it starts vibrating. So when you are dragging, how you are going to drag, that decides how you are going to get the oscillations. So that displacement is given in this particular format of mu x into L minus x. So 4 different arbitrary constants and 4 different boundary conditions we have got it. Clear, Avinash? Okay, fine. Now actually, so substitute the first boundary condition. I take this as the first condition, this as the second condition, this is the third condition, this is the fourth condition. So first condition, if I substitute it, then this is y of 0 comma t is equal to, so x is 0, that means c1 is 0 and c2 cos px, so cos px is 1 and then c3 sin cpt plus c4 cos cpt equal to 0. It implies C2 equal to 0. This is one condition. And the second condition is derivative of this. So now the equation is y of x comma t is equal to, so C2 cos Px into, C2 equal to 0, right? So then C1 sin Px and then C3 sin Cpt plus C4 cos Cpt. Now we take the derivative with respect to t. So that is dy by dt at t equal to 0 is going to be c1 sin px c3 into cp into derivative of sin is cos cpt plus c4 Cp into derivative of cos is minus sin Cpt. And this is again equal to 0 at t equal to 0, right? Now if you substitute t equal to 0, C1 sin Px and then C3 Cp into 1, because t equal to 0, cos of 0 is 1 minus, so this is 0 and this is coming out to be 0. So this is possible only if C3 equal to 0. But what if I take C1 is equal to 0? What if I take C1 is equal to 0? Anybody? What if I take C1 is equal to 0? Yeah, exactly. It is going to vanish. If I take C1 is equal to 0, then C2 also is 0 and C1 is also 0. Then this entire function is going to vanish out. So that's exactly the reason. So C2 you cannot take as 0. So C3 equal to 0. Then function is going to be y of x comma t is equal to C1 sin Px. And then C3 is coming out to be 0. Then C4 into cos Cpt. So this is the equation we have got. So two boundary conditions are over. Now the third boundary condition is this equation, that is y of L comma t is equal to 0. Then if I put that one, third equation, y of L comma t is equal to C4 C1 sin PL cos Cpt equal to 0. Now this equation is equal to 0 if sin PL equal to 0. It implies sin n pi, which is the general solution for 0 of sin value. Now PL is equal to n pi. PL is equal to n pi and P is equal to n pi by L. P is equal to n pi by L. Got it? So note down till this point. And which is the last boundary condition we have to put it. That you need to understand as a special case now. The last boundary condition. Note it down. Note it down. Okay. Then the last boundary condition is so final solution whatever we have got is, that is y of x comma t is equal to C1 C4 sin n pi by L times x cos n pi c t by L. So this is the equation what we have got after substituting all the three boundary conditions. Now one last boundary condition we have to substitute. Now I call this as, so this is actually, there is something called n comes into picture. So this is going to be Bn times of sin n pi by L times of x cos of n pi c by L times of t. Now this is the condition. Here actually I have brought in the picture of Bn and then putting a sigma n is equal to 1 to n. Why we have kept in this particular format is, as we know from differential equations, right? So suppose actually if you take a second order differential equation, the auxiliary equation is m square, let us say m square minus 5m plus 6 equal to 0. Let's say this is the auxiliary equation. Then the solutions of this is m is equal to 2 and m is equal to 3. Now if this is the case, you will write the complementary function as c1 e power 2t or 2x, whatever it may be, plus c2 e power 3t. This is how you write it. Now actually, this is one term and this is one term. In between, actually, you have put a sign of plus. So, does anybody aware of why you are putting in this particular format? Why we are putting two different terms and then putting plus in between? Ideally, actually, there are two different solutions here, right? Two factors are there, but still we are putting it as plus in between. So, any one also you can take as a solution. So, in case of differential equation, the most generic form of the differential equation, what we are putting it is, that is, m is equal to 2 is one solution, m is equal to 3 is another solution. The sum of these two again a solution to the original differential equation. That's exactly the reason we put this one and this one. This is one solution and this is another solution. Got it? So this solution, how we have got in this particular format of c1 e power 2t is, so this you have to solve as if like it is a factorized. That is d minus 2 into d minus 3 of z equal to 0. So here actually you have to form this differential equation and solve it. And then whatever the value you are going to get it, you have to form one more differential equation and then form it. Then you are going to get this solution. So individual solutions is also a solution, and combination of all together with a sum is again a solution to the original differential equation. Now here also exactly the same case what we are doing it here. This is n pi x by L and n pi ct by L. So here n coming into picture, which is a new variable. That n actually, for different values of n actually we have different solutions. Now the sum of all the solutions together will also be a solution to the original differential equation, which is the most comprehended solution. The way we have done here, two different solutions are there. Now if you put it and add it together, this is the comprehensive solution for this differential equation, rather than putting only c1 e power 2t or c2 e power 2t. Got it? Understood? Understood or not? Yeah, so that's exactly the reason actually why we are putting here sigma. So that means there are n solutions are there, which essentially means that this n will be almost infinite. That means for each n value you are going to get one solution. What it physically means for us, that physical significance to this is, so this is one waveform which was given initially. Then after some time, like actually when you give the initial displacement, then actually it is going to produce one more waveform like this, and then one more waveform like this, and one more waveform like this. Now all the waveforms together at any instant, if you add it together, that will be leading to the actual displacement at that particular point. Now, so there are infinite number of waveforms that are generated for a single displacement, and all the waveforms together will lead to a single value there. So that will be the actual position y of x comma t at any location and at any time t. Got it? And all these things are called as the harmonics. Harmonics of the waveform. Got it? Yeah. So now actually based on this understanding, this value is y of x comma t. Now if you want to find out this bn value, this value will be different for each n value. Right? For each n value, this constant may be different. This is an arbitrary constant. This arbitrary constant we will be able to find out with the help of the initial condition given by the initial displacement. This initial displacement will decide what should be the number of harmonics and what should be the shape of the harmonic. Everything is getting decided by only with this initial displacement. This initial displacement is nothing but at t is equal to 0, the location y of x comma 0 is equal to sigma n is equal to 1 to n and bn cos of n pi x by L. So where the x will remain and t will be 0. This is sine of n pi x by L, and then this value is going to be 1. And this is exactly the Fourier series. So this value y of x comma 0 is nothing but mu times of x minus mu x into L minus mu x square. Yeah, minus mu x square. This is equal to n is equal to 1 to n bn times of sine n pi x by L. So this is what is called as the Fourier half range sine series. This is the standard form of Fourier half range sine series. I hope you are aware of what is this Fourier series. A Fourier series is a beautiful tool. So this is an excellent tool like Maclaurin series. So Maclaurin series actually has the ability to transform any nonlinear function or any function, whatever you can give it, that will be translating into a polynomial format. So and then we have very wide range of research that was done on polynomials in mathematics. That means if you are able to express any random equation into the polynomial format, you will be able to analyze very easily. With almost 98% of accuracy, you will be able to analyze any random function given if it is in the polynomial format. So this one, that is the Maclaurin series, will give the ability to convert any random function, maybe a sin x, maybe e power x, maybe log x, or whatever it may be you can think of, that actually Maclaurin series will be able to convert into a polynomial format. That will be the greatest advantage of Maclaurin series. That's why actually it is one of the fundamental theorem which will simplify our mathematics. That is one such kind of series. And exactly in the similar manner, there is one more form of the series format. That is the Fourier series, which will be very, very widely used in signals and systems. For the signal analysis purpose, actually, we will be using the Fourier series and the Fourier transforms. So this excellent tool, what it will do is, given a random function, so in this case, mu x into L minus x. So you give me any random function of your own, then I will convert that into the sum of sines and cosines. So in the case of signal analysis, it will be easy for us to analyze with the help of complex analysis if it is in the form of sines and cosines. That's exactly the reason why actually we need a tool called Fourier series to convert given a random function into the sine and cosine series format. So that tool is the Fourier series. So here it has got lot of features, but out of that, whatever is needed for us is the Fourier half range series. That half range series is, it should contain only the sine terms. Then only we say that the half range Fourier sine series. Suppose if it is cos, then actually we have to be converting into the half range Fourier cosine series. Ideally, Fourier series will contain both sine and cosine terms with two different constants getting multiplied. Now each constant will be different. Bn, so n is equal to 1, n is equal to 2, n is equal to 3. Each value may be different, that depending on this particular function what you are going to get it. Now here in this case, mu xl minus mu x square is the function. So for this actually we have to identify this bn value. So he has given a way to find out this bn value given by 2 by L times of integral 0 to L. This function, that is mu xl minus mu x square into sine of n pi, so this one, sine of n pi x by L into dx. So this value will directly give the bn value. Got it? Now actually it is up to us how to find out the integral of this. So there is a beautiful method to find out the integral of this kind. That is, suppose if you have udv format, then this can be directly found. That is without even applying the by parts or the extension of the by parts principle. That is uv minus u1 v dash plus u2 v double dash minus u3 v triple dash. So minus plus dash 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 up to infinite or till the end. So this is u is the straightaway multiplication and v is nothing but integral of this, and then derivative of u is here and integral of this v is here, and again the derivative of this is here and the integral of this is here. Now the product of the derivative and integrals multiplications together, it will continue till one of the thing actually has to vanish out. And then in between the signs are minus plus minus plus. These should be the alternative signs, right? Now usually the derivative part actually you have to select such a way it should vanish out. Now actually take this particular function. If you take the first derivative, then mu L minus mu x, 2 mu x, that is the first derivative. If you take the second derivative, then the first term is going to vanish out and the second term is 2 mu. And if you take the third term, the term is going to be 0. So then the series is going to end there. Got it? So this principle you can make use. This is an extension principle for the by parts. Got it? In integration. So note down till this point and then I am going to erase it here. Note it down. Done? Okay. So this Fourier half-range sine series, you have to find out this constant value Bn. So that Bn value so this is Bn is equal to, so u is mu xl minus x square, mu x square, u into v. V is nothing but the integral of this. So integral of this is integral sin x minus cos n pi x by L divided by n pi by L minus derivative of this is mu into L minus 2x, and then integral of this is minus, so integral cos is sin. Sin n pi x by L divided by n pi by L whole square. And then plus derivative of this is minus 2 mu, and the integral of this is, integral sign is minus cos. So that is cos n pi by L, n pi x by L divided by n pi by L whole cube. So upper limit is L and lower limit is 0. Now if you substitute the upper limit, this is mu times of L square minus L square. This is going to be 0. So this is going to be 0. Just a minute. Yeah. So then minus of, so mu times of L minus 2L. So this is minus L. So this is sin n pi. This is going to be 0. And then plus minus 2 mu times of upper limit is cos n pi divided by n pi by L whole cube. Got it? So minus lower limit is, so this value is 0 and this value mu L times of 0. So this is also 0 plus so the last term is, if I keep it 0, minus 2 mu times of 1 by n pi by 3 or n pi by L whole cube. So this is after substitution of the limits for the Bn value. Got it? So once you substitute these values, so this is 0 and this is 0. This is minus 2 mu cos n pi divided by n pi by L whole cube, and then minus of minus will be plus 2 mu divided by n pi by L whole cube. So this is the Bn value. Then if you take 2 mu out, then 1 minus, so this is cos n pi is minus 1 whole power n divided by n pi by L whole cube. Got it? Yeah, let me check the answer once. So this is correct only. So here actually, so 2 by L is left over. You have to add that 2 by L. So into 2 by L. Yeah. So here actually, this you can further simplify as 4L square mu by N cube pi cube into 1 minus 1 whole power N. Got it? Understood? If you want actually, you can further simplify this actually. For every even number, this is going to vanish out. For every odd number, this will become twice. Correct or not? Got it? So that way actually, you can keep the odd number, that is, so this will become 2 times, that is odd number, then 8L square mu divided by 2m minus 1 whole cube into pi cube. This is the m value. Got it? So this is, for every even number it is going to be 0. For every odd number actually you are going to get the value twice. That is 1 minus of minus 1. That will be plus 2. So 2 times of that, 8L square mu divided by 2m minus 1 whole cube into pi cube. This is the Bn value. Now the same Bn value you have to substitute even in the original equation. So note down till this point. I am going to erase it and write it in the complete form of the equation. So this 1 minus 1. So I hope you know how I have written this minus 1 whole power n. Is that clear? Minus 1 whole power n. No. Okay. See this cos n pi value, sin n pi is always coming out to be 0 irrespective of the n value. So the n value, if it is 1, 2, 3, 4 or whatever it may be, sin pi is 0, sin 2 pi is 0, sin 3 pi is 0, sin 4 pi is 0. Similarly, cos n pi, what happens is, this value is going to be minus 1 whole power n. Why? Because, so if n is equal to 1, the cos pi value is minus 1. If n is equal to 2, cos 2 pi is plus 1. Suppose if n is equal to 3, cos 3 pi is again minus 1. That means for every odd number it is going to be minus 1. For every even number it is going to be plus 1. That's the reason when we write cos n pi, immediately minus 1 whole power n, we will write it straight away. So here the cos n pi factor is there. So this cos n pi I have replaced with minus 1 whole power n. Understood now? So once we got to that, then actually we know that for odd number actually this is going to be minus 1. For even number it is going to be 1. Now for even number 1 minus of 1 is going to be 0. For odd number 1 minus of minus 1 it will be 2 times of that. So that is 2 times of 4L square mu divided by n cube pi cube. That's why if you replace n is equal to 2m minus 1, so 2m minus 1 is always an odd number. So if you replace it there, this is going to be twice and no matter of worrying about the even numbers because 2m minus 1 will comprehend. Got it? Note down this. Yeah. Done? Note it down. Okay. So once you note down this, so this value you can put it in the final equation. That is, the final equation what we have got is, so that is y of x comma t value is going to be sigma n is equal to, so here actually instead of n now it is m is equal to 1 to m, then 8 pi square, so 8 L square mu divided by 2m minus 1 whole power 3 into pi cube into sin of n pi x, n is 2m minus 1, pi into x by L cos of, so n pi ct, so that is 2m minus 1 pi into c into t divided by L. Got it? So this is the final solution. So this is what actually he asked us to find out. Here, any questions? So usually actually it will take a lot of time. Usually there is very high possibility that you can make mistakes in Fourier series. So that's why actually try to put it in the optional format. That is, so you try to manage without doing this. Suppose actually if it is mandatory, then only actually you go for this. So the problem with this is, it is actually mandatory, you will be able to solve it, but very high possibility to make the mistakes in calculating the Fourier series. Got it? The simplification of the Fourier series is not so easy. So if it is straight away sin x or cos x or mu x or nx format, you might be able to do it within a short time. But suppose if the equation is of this particular format, suppose if this is given in this particular format, that is initially the string was stretched like this and left it, then actually it is going to oscillate like this. Then in such cases, you have to take till this point one function, from here to here another function, from here to here another function. You have to divide the function into 3 different parts, and then for that 3 different parts actually you have to do the Fourier series. Got it? So that will be a little bit tougher and it will be very, very lengthier. So I suggest not to attempt such kind of questions because it will take a lot of time, though you know the procedure. Got it? Procedure is not very tough, but the problem here it is, it will take lot of time, not lesser than half an hour it will take. And heat equation. So vibrating string. Now let us discuss the heat equation. I'll just divide heat equation. So this equation is going to be used in case if you wanted to identify the heat flow at any time and at any displacement. Suppose let us say there is a rod like this, and this particular rod, let us say initially it was given certain heat. So given by that equation, some random equation f of x. And then suddenly what he says is he immersed both the ends into the water. Then suddenly he makes the main, so this temperature equal to 0 and this temperature also equal to 0. And then he tries to maintain there. Initially it was given the function f of x, which is nothing but the heat distribution at any time. So this one f of x comma 0. Then he will be asking us to find out at any value of u of x comma t, what will be the temperature at any random point and at any time t. So this is exactly the same case of the heat wave equation, whatever we have done now. So the same procedure, same methodology. Even for the Laplace equation also, it will be the same procedure and same methodology. But only thing is the initial conditions may differ. Got it? So here actually we will take one heat equation and then let us find out the general solution of the heat equation first, and then we can go further on this. First of all, the wave equation, right? Exactly it follows the heat equation. Now this heat equation, it will be dou u by dou t is equal to c square times of dou square u by dou x square. So this will be standard heat equation. This is the standard heat equation. So this standard equation solution, now actually assuming the solution to be so that is u of x comma t is equal to x of x into t of t. So assuming that the product of these two will give the solution for us, then dou u by, so simply I will write this as u is equal to xt. So where x is a function of x alone and t is a function of t alone. Now if you apply in this, so dou u by dou t is equal to, so that is x into t dash. Similarly, dou u by dou x is equal to x dash into t, and dou square u by dou x square is equal to x double dash into t. So if you put it in this equation, that is dou u by dou t is xt dash is equal to c square times of x double dash t. And then if I bring this to here, that is t dash by t is equal to c square times of, or actually I will put this c square here, c square t is equal to x double dash divided by x, and I call this as some constant k. Exactly in the similar manner we have done in the wave equation. So let us assume k is always positive. So 3 cases we take it, and then from that actually we will pick up the appropriate. So that is always positive. If k is always positive, then so k is equal to p square, because P is always positive value. Now if you put that equation, that is case 1. Case 1 is going to be T dash by C square T is equal to P square is one equation, and X double dash by X is equal to P square. This is another equation. Now T dash equal to PC whole square into T, or T dash minus PC whole square into T. So this is equal to 0. The auxiliary equation is M minus PC whole square equal to 0, or M is equal to PC whole square. The solution is going to be, so that is the complementary function is this one, C1 e power PC whole square into T. Got it? And exactly in the similar manner, this is X double dash minus XP square equal to 0. The auxiliary equation is M square minus P square equal to 0. Then M is equal to plus or minus P. So M is equal to plus or minus P. Then the complementary function is C3 sin Px plus C4 cos Px. So this is a complementary function. So then the final solution is going to be, so for case 1, it is case 1 C1 e power Pc whole square into T into C3 sin Px plus C4 cos Px. So this is the solution of the partial differential equation. Got it? And then we have to take the case 2, that is if k is equal to minus p square, that means which is always a negative value, then what is going to be the solution? Sorry, so I think so there is a mistake here. C3, the solution is, here it is a positive value, right? So C3 e power px plus C4 e power minus px is the solution. So because the roots are real and unequal, then this is going to be C3 e power px plus C4 e power minus px is the final solution of the partial differential equation. Got it? Now we have to take the second case, that is if k is equal to 0, what happens, and if k is equal to negative, then what happens? You note down this is the first case, then I am going to solve for both the two cases. Note it down. Done? Being the RHS part is 0, there is no need to find out the particular integral, because the particular integral will be 0. Because on the right hand side it is 0. Here also 0 and here also 0. Only the complementary solution will be the final solution for us. So this is, what is U in the standard equation? So U is nothing but the heat. So heat as a quantity, we will calculate this. Got it? Or sometimes actually it may be temperature. So this T is, so this is time and this is displacement. So this U may be either heat energy, or maybe temperature. So it can be given for both. So that is out of scope for us. That is actually most advanced level. Deepak. So these equations, the wave equation and the vibrating string equation, heat equation and the Laplace equation, these equations derivations are in the physics, not in the mathematics. Got it? So based on certain physical scenarios, actually they have developed these equations. Some are actually, even the Laplace equation came from the Maxwell's equations. Got it? So that's why actually we have only the applications of this, which are nothing but the solutions of these equations, not the formation of the differential equations. Got it? Okay. Okay, so then case 2, if you take it, then t dash by c square t is equal to minus p square. This is case 2, so where a is equal to minus p square. So this is case 2. Then in such cases, then this value and the other equation is x double dash plus x p dash p square equal to 0. This is the second equation. Now the solution of this is, so t dash plus cp whole square into t equal to 0. And then here it is, so x double dash, or the auxiliary equation is m square plus p square equal to 0. And this is m is equal to plus or minus ip. So if this is the solution, then what we are going to get it is, this x value is c1 e power c1 sin px plus c2 cos px. So this is going to be the solution because this is imaginary. For imaginary roots to the complementary function are going to be sines and cosines. Now in the similar manner, here also this is m plus cp whole square equal to 0. M is equal to minus cp whole square. The solution is going to be t is equal to c3 e power cp whole square into t minus of. Now the final solution is going to be u of x comma t is equal to, this is going to be c3 e power minus c square p square t getting multiplied by c1 sin px plus c2 cos px plus c2 cos px. So this will be the preferred equation. Anyway, I am going to solve it for the next one. Yeah, exactly. So everybody knows, this is universally aware of this one, the wave equation and the heat equation. So these are actually, everything is known. Got it? Got it? Any questions? Now, the case 3 is, that is if k is equal to 0, then this is going to be t dash equal to 0, and here this is also x double dash equal to 0. Then x dash equal to constant c1 and x is equal to c1x plus c2. So this is the solution, and here t equal to some constant c3. Then the final solution is going to be u is equal to xt, which is nothing but c1x plus c2 times c3. So this is the final solution. So this is a ruled out solution, and the first one is also a ruled out solution. And then this is the preferred solution because it should involve the transient components. That is one thing. So here actually e power minus c square p square t. So this is going to die out after a certain time, because as t goes on to infinite, this value is coming out to be 0. So if this is value is coming out to be 0, obviously the temperature value is coming out to be 0. Got it? Clear? Any questions on this? So this is the most preferred solution out of the entire heat equation. So out of 3 cases, we will be picking up this as the standard equation. Clear? Any questions on this? Any questions on this? Okay, so if there are no other questions, so I'm going to stop the class for today. In the next class, actually, we're going to solve some problems based on this heat equation, and then let us see if we can start with the Laplace equation in the next class. Yeah, so is that fine? Yeah, so that's all for today. Thank you. Good night.